Today we are going to discuss about two issues as mentioned earlier. So first issue is about construction stage analysis, and the second issue is floor diaphragm analysis, floor vibration analysis. So let's start with the construction stage issues. So in the high-rise building, the actual deformation of the column cannot be ignored. So that's why we need to consider the construction stage analysis. So we know that why we need construction stage analysis. That load is not the load which will be applied at once. So it is like the sequential loading. So its effect is different when we consider it as a conventional analysis and when we consider it in the construction stage analysis. So this is the comparison with the conventional analysis and when we consider the construction stage analysis. So in this 60-story building, 40-story building, this shows the moment of the column. So this blue color represents the conventional analysis without considering the construction stages. So when we consider the time-dependent effect and the construction stages, then its moment can be different, as you can see this much, which is about 40%. So for the high-rise building, which is more higher than 30 or above, we normally consider the construction stage analysis. Construction stage analysis is required for the compensation of the differential column shortening. Column shortening occurs because of these factors like elastic stress due to gravity load and creep caused by gravity load and shrinkage and temperature variation of the exposed column. So if you see this table, this shows the column shortening for the steel structure and concrete structure. So due to the elastic shortening and creep and shrinkage, we can see how much it occurs when it is the 80-story building. The effect of the column shortening can be divided into these two non-structural and structural effects, and as we know, the structural effect is the major issue we need to consider. So it can occur the distorted slab or beam due to the differential movement, and gravity load will be redistributed. So shortening can be divided into two different parts. One is pre-slab installation shortening, which occurs up to the time of the slab installation. And the other one is post-slab installation shortening, which occurs after the time of the slab installation. So when our desired level is like this, and then we can expect the pre-slab installation shortening and post-slab installation shortening separately. And depending on the structural type, we need to have a certain compensation. It is different for the RC building and steel building. In case of the RC building, by adjusting the formwork, we can ignore the pre-slab installation shortening because it will be adjusted by the formwork. So when we do the compensation, we only need to consider the post-slab installation shortening. But in case of the steel structure, we need to consider both pre-slab and post-slab installation shortening. So depending on the structure type, we can check the column shortening for the pre-slab, post-slab, or the summation of the post and pre-slab shortening. So both is provided in MIDAS. We will check with the program. So this will be the procedure when we do the column shortening analysis. So firstly, we will use the certain material and section property loading data, which assumed the beginning of the construction. And then during the construction, we do the experiment, and then we need to update the material property like the elastic modulus, creep, and if there is tendon, pre-stress loss needs to be adjusted in order to reduce the errors between the measured shortening and the analysis results. So during the construction, we need to keep adjust these factors, and then we will do reanalysis again to minimize the error, to have the best fit of the column shortening with the field data. So I will briefly show you some of the application of the high-rise building with the practical models. One of them is the SK Trenyu building in Korea. So this is the building. After I explain these general features, then we will see the step-by-step how we can make this type of the model using our sample model. So this building is composed of the 63 floors, and this is the composite frame composed of the RC and steel structure. And the ground level is, if we see, this is the ground level. And if we check the construction stages, firstly, it starts from the base core. After that, the first basement is installed with the retaining walls, and then by the top-down method, it is constructed. So after the basement is completed, and then we start the superstructure. In this structure, we can see the steel frames, and we want to consider the composite member. So outside of this steel frame, we want to cast the concrete. So if we check the next stage, the column has now the concrete, so it has the composite action. And in the next stage also similarly, the column was previous step, it was bare steel, and now we have the concrete. This can be considered using the composite section for construction stage data that I will explain later. So MIDAS Gen can consider these different stages for considering the before composite and after composite action. So if we see the data, For the part 1, which is the bare steel, and part 2, which is the concrete part, we can specify the different activation stage in here. So stages will go like this. And at the middle of the structure, we have the outrigger truss. If you see here, we can see the truss. And for simulate this X truss, we used the truss element, so it resists only the axial forces. So there is no special method when we consider the outriggers. We can simply model them using the truss element or beam element with the certain stiffness of their member. So after certain days, then it is finally completed. So each story installed one by one for the different stages up to the final story. And MIDAS Gen has the special element type, which is called wall element. Gen also have the shell element, in-plane or out-of-plane type shell element, but also wall element is provided, which is suitable for the high-rise building mainly. So when we use the wall element, if we see one certain story, for example, so one wall element in one certain story, it should not be divided in the vertical direction. So wall element should be continued in one floor, as you can see in this. And the advantage of using wall element is the analysis time and modeling time will be significantly reduced. So if we go to the create element feature, there is the wall. So we can consider it as a membrane type or plate type by specifying certain thickness and material. Then by clicking 4 different nodes, then we can create the walls. So in case of the high-rise building, the analysis results will be very similar to the shell element. So as I mentioned, advantage is time of the analysis and modeling. And as you can see in the construction stage analysis, we considered the time-dependent material like creep shrinkage and elastic modulus. Firstly, if we go to the time-dependent material field, we can specify the desired code like CBFIP, ACI, and Europe code. All user-defined creep function can be defined. So by specifying its compressible strength and the related data, then we will have the creep coefficient function and shrinkage strain function. And this data will be used during the analysis. Similarly, for the elastic modulus, we can specify the database from here. And then by entering the compressible strength, we can consider the changes of the concrete strength. So how to use this data, how to use the creep shrinkage and compressible strength is just like the conventional analysis. We will have the certain material property, and then by making the link between the material and creep shrinkage, like for the creep shrinkage function, compressive strength function, and the elastic material property. By making the certain link, then they will be used during the analysis. Also, we have the section stiffness scale factor. So this can be activated in a certain stage. For example, in this model, at 44 stage, we wanted to consider the certain reduction of the section property for these columns. So this is generally used when we want to consider the when we want to reduce the stiffness for considering the crack or some other reason. So this can be activated in the certain stage and its stiffness will be recalculated. In MIDAS 10, how to make the construction stage, we will do with the sample model, but if I briefly explain, this is the construction stage data dialog box, which is composed of the element, boundary, load tab. So by activating or deactivating certain element group and boundary group and load group, we can make the construction stage. So one by one, we can create the stages with the certain duration. And then for each stage, we will have the construction stage. If we check one other model, this is the Hanoi Landmark Tower. So this building is composed of one building is 70 floor and the other one is 49 floor. This building is for the 49 floor building. So if we see, you can see the core walls and the frames outside. And if we check with the stages, so previously the previous building was top-down method, but this time it starts from the bottom of the basement and then construction goes like this. So each stage, one by one, each story is installed. And finally, it is constructed like this. In the middle of the building, similarly, we have the outrigger truss. So this member is also the simple beam element. So by modeling the beam element, this outrigger has been represented. And similarly, the time-dependent effect has been considered. And we can release the moment for the sub-beam. So at the basement, when there is the sub-beam, we release the moment using the beam end release feature. So modeling of the construction stage analysis is not very much different from the other type of the analysis. Firstly, we make the entire structure, and then we need to have the certain group for the structure, boundary, and load to be activated or deactivated during the stages. After that, as I mentioned, by activating or deactivating them during the stage, we can make this construction stage analysis. And then we do the time-dependent effects. There is the construction stage analysis control data. So from here, we can consider the time-dependent effect. So as a default, it is considered. And nonlinear analysis can be considered during the construction stages. So if there is a cable in our structure, we can also consider the large displacement analysis with the construction stages and with considering the creep and shrinkage effect. And here is the one feature, load case to be distinguished from the dead load for CS output. So as a result of the construction stage, if we go to the certain result, it will show us the dead load, live load, creep, shrinkage, and summation. Actually, when we define the load, we had the different type of the stating load case. Dead load, live load, superimposed dead load like this. But when we check the results, all the dead load, even the live load, will be merged and summated in the dead load CS load case. But if we want to check the live load effect separately, in that case, we can select the live load and add it in here. So this live load will be distinguished from the dead load, which means live load effect, live load case will be shown in this load case, CS live, and other dead load will be summated in the CS dead load case. And apart from this, creep and shrinkage effect can be checked separately, and then summation of these four will be shown in here. So if we do not specify this data, which means there is no load case which will be distinguished from the dead load, in that case, zero results will be obtained in the live load case, and entire dead load, live load, everything will be merged in the dead load CS load case. Okay, let's go back to the presentation. So, procedure of the construction stage analysis. As I briefly mentioned with the model file, so making the construction stage model is not complex in Gen. Making the material, section, and geometry is same as conventional analysis. And then we need to make the group so that it can be activated in each stage. So make the elements group, boundary group, and load group. And then we can consider the time-dependent material. As we checked, we can use the database or user-defined function for the creep, shrinkage, and compressive strength. And then we will make the construction stage data for each stage. After that, we can perform analysis, check the results, forces deformation, and the column shortening results, so on. So we briefly had a view for the time-dependent material, creep, shrinkage, and compressive strength. So if we go to the model again, so when we use the database, then we can just enter the required fields like the compressive strength and relative humidity, volume surface ratio, so on. And if we use the CBFIP standard, also similarly we can specify the compressive strength and notational size, cement type, and age of the concrete at the beginning of the shrinkage. So for any database, we always need to enter the start date of the shrinkage. When we use the ACI or CBFIP, there is the field for the age of the concrete at the beginning of the shrinkage. So when the shrinkage will be started, we can specify the date from here. And as I mentioned, we can use the user-defined creep function. We need to be careful when we use this user-defined function. So we can specify the function by ourselves in this table. So we can simply copy and paste a certain function from here, or we can directly enter the value from here. And when we define the creep function, we need to define the several functions, not only one or two functions. So with the different loading age, because each element will have the different loading age. So depending on the different loading age, like the 1 day and 3, 5, 10, so on, with the different loading age, we need to define the several user-defined creep function. And then, for example, let's assume we have defined user-defined function for loading age 1 day, and the other one is 5 days. And one of the elements loading age will be 3 days. In that case, program will do the linear interpolation. So if there is only one function and program cannot do properly for the interpolation, which means the analysis results cannot be accurate. So in order to have accurate results and in order to have better convergence in the creep analysis, we need to have the several user-defined creep and shrinkage creep function when we use the user-defined type. And we can specify the compressive strength. So for here, ACI, CBFIP also same. And when we use the CBFIP creep and shrinkage, we need to have the notational size. That notational size can be automatically calculated by the program. If we go to change element dependent material property. Also in ACI, we need to calculate the volume surface ratio. So this can be specified for each of the element using this change element dependent material. And notational size for the CBFIP can be automatically calculated for entire structure. So by selecting all of the elements and then by clicking apply, the notational size based on this equation, the H value will be automatically calculated. And when we make the construction stage data, so we use this dialog for each of the stages. As I mentioned, it is composed of 3 different types: element, boundary, and load. So if we go to program again, firstly, in the element tab, there is the structural element group and the age. So this age is the day from the concrete is casted. So until the formwork is removed, it will not have the certain stiffness. But we want to consider the time-dependent effect like creep and shrinkage and changes of the elastic modulus. So let's say if the duration of the first stage is 32 days, and then before starting of this stage, 2 days before, this element group has been casted, and then after 2 days, this element is activated, so it has the certain stiffness. So this age is not included in this duration. So this age is before the duration days of the certain stage. So for considering the time-dependent effect, we can use this age properly. Also, if required, we can deactivate the certain element. When we do the deactivation, there is the option for the element force redistribution. So during the construction stage, if we want to activate some temporary element, and then next stage we want to inactivate that temporary element. In the case, we can just bring the corresponding element group to the deactivate field. And then the forces which was applied to certain element will be redistributed to the connected element. During this redistribution, whether we want to redistribute 100% or 50%, we can specify the percentage in here. So generally, when one certain element is deactivated, 100% of the force should be redistributed to the connected element. So 100% is default. And if we move to the boundary, we can also activate or deactivate the boundary group. And there is the option original and deformed. When the deformed is selected, let's say in certain position we have the boundary, for example support, and next stage, in the conventional analysis, its support location will be different from the construction stage's support location because of the deformation from the self-weight. So when the node position is changed, whether the boundary will apply to the deformed position, or if we want make certain specified displacement, and then we want to assign that boundary group in the original position, which was the initial modeling position. So as we want to have the accumulated results for the construction stage analysis, deformed option should be generally used. Original is required especially for the bridges when we use the incremental launching method, when the support position is already fixed. In that case, we use the original. But in the building, generally, we always use the deformed activation for the boundaries. And in the load tab, also it's same. Load group will be shown, and we can click Add to bring it to the activation or deactivation. Load can be activated in the first day of the stage or last day of the stage. Also, we have the additional step option in here. So additional step option is only for the load. So if certain load needs to be activated during the certain stage, for example, we have entered the additional step for 10, 20, 30 days when the duration of this stage is 32. So we can activate certain load in the 10th day or 20th, 30th, even the last day of the stage. So if there is no changes in the element, activated element, and only certain load needs to be activated during the stage, we do not need to make the new stage. We can just use this additional step. So again, if we move to the presentation, in a certain stage, we can add the additional step during certain stage. So this additional stage can be used only for the loads, adding the load during one stage. If there is any change in the element, we should always make the new construction stage. We cannot use the additional step for the element group or boundary group. And here save results option is there. So as a default, stage is checked on, which means that each stage results will be saved, and then we can check the results for one by one each stage. Also, there is another option, additional steps. So this additional step, when we want to check the forces or deformation of the additional step, then we can check on this option. In this case, when you check the certain forces, for example, in some stage, we can specify the additional step from this step field. First step or last step and the additional step. If we do not check on this additional step, program always give the each stage results according to the last step only. So if we want to check the first step results, even though we do not have the additional steps, if we want to see first step, not only the last step, in the case, we can check on this additional step option. And we have one summary table for the activation of the group. Under the query, if we go to group activation of the construction stage, we have 3 different tabs: element, boundary, and load. So we can see with the one view which element group has been activated or deactivated. If there is any element deactivated, and then X mark will be shown, and so A represents the activate and T represents total. So as a total status, if there is any group which is not activated, we can check it in this table. Same for the boundary and load. When we use the construction stage model, we will see very common base stage, post CS, and each construction stage. So after performing analysis, we can see one by one each stage, and also at the end there is min-max stage, which gives the minimum or maximum result, and post-CS. Post-CS represents the member forces or deformations obtained from the last construction stage, and in this post-CS we can make the load combination. So for certain load which is applied after the construction, like the wind load or earthquake load, if we want to consider, then we can apply this load, and the load will be considered in this post-CS only. And base stage is, as you know, this two is moving after analysis state, before analysis state. So in this, we call it as pre-processing, and we call this as post-processing. In the pre-processing, we can see the base stage. So base stage is just for the modeling purpose. So if we want to change any data in our building, we always move to the base stage and make the modeling. We cannot make changes in the model by selecting certain stage in here. Program will give you error message in the message window. You should move to the base stage. So when you work with the construction stage model, then if you want to add some data or modify some data, you always move to the base stage. So as I mentioned, we can check the results for each of the stages. As this model is quite large, so it takes some time. So let me open the simple model to show you the results. So this is the tutorial model. And using this model, for example, if we want to check the beam diagram for the final stage, dead load, as you can see, we have only last step results in here, no first step or no additional step, because we did not check on this option. So if we want to check the first step forces, we need to check this option. So we will see the last step results due to the dead load and live load. So in this model, we have made the load case to be distinguished from the dead load as a live load case. So this load case, which was in here, due to this load, the forces has been shown in this CS live load case. And then creep, shrinkage, and or summation. These results can be checked for each of the construction stage. And also we can check the minimum maximum results as I mentioned. So Bmax forces for each of the element we can check. So you may know if we want to check more details, we can go to the tables. For example, I want to see the summation. I can specify desired stage in here, or I want to check minimum maximum value. So we can see the minimum and maximum forces in here. So each of this stage and the min-max stage, we can check the results. It's same for the deformation and stress. Also, if we want to check the certain value of the minimum maximum, we can see minimum maximum value only. So min-max value can be checked with the value as you can see in here. Finally, we can check the column shortening graph. As I mentioned at the beginning, column shortening is composed of two different factors. One is post-slab installation. The other one is pre-slab installation. So post-slab installation is the shortening after casting the slab. Pre-slab installation is before casting the slab. In MIDAS Gen, as you can see in this dialog box, we just mentioned sub or up. So sub is the short term of the subsequent slab, which is the after casting the slab, and up is up to slab. So before casting the slab. So as we know, when we check the column shortening for the RC structure, we need to check after casting slab, which is the subsequent slab. And when we check for the steel structure, we need to have the summation between two. So here TTL is short term of the total. So total shortening, we need to check for the steel structure. So if we check it with the model file, under the results, we can see the column shortening graph for CS. So we can specify the desired position of the member. For example, I want to check this column and its location is X direction 27 and Y direction 10.2. So add a new column. I want to name it as column 1. Since this is the IC structure, we only need to have the after casting slab shortening, so which is the subsequent. For the elastic shortening, clip, shrinkage, and summation of these three components. So column 1 is added in here. We can specify desired stage. So we can see the column shortening graph for the clip, elastic shortening, shrinkage, and the summation of these three. This column shortening results can be saved as a text, so we can see the detailed value from the text results. There are some more features that I want to explain. In the construction stage analysis, so I have mentioned how we can make the construction stage data manually. So we can specify the different structural group one by one, first story, second story, because they will be activated in the different story. And the boundary group and the load group, one by one, we specify different groups. For the boundary or load, for example, for the Pimentel lilies, when we enter the boundary, we can specify the group in here. So proper boundary group can be specified from this field. Or if we move to the table, we can specify its group for one by one. So boundary group, and also similarly for the load group. If we go to the floor load table, we can specify the load group in here. So that is the manual way of making the construction stage data. But there is another way. It's using the wizard. In the wizard, if the construction goes in a certain rule, like one by one story with the same duration, in this case, we can use the wizard. I will use the wizard in the following demonstration. And I mentioned the composite section for construction stage. So from here, when we use the composite member, we can consider the different construction stage for only part 1 and part 2. So composite action can be considered in the different stage. And we can check the stiffness only for the part 1, before composite action and after composite action, we can check different section stiffness, and that stiffness will be applied during the analysis. When you use the manual modeling for the construction stage, we can freely assign certain elements in a certain group. So, like the auto-climbing frame system, like wall is installed first and frame is installed after a certain story. This can be freely generated in Gen, because what we need to do is just defining the group for the activated elements. And previously with the model, I showed you the section stiffness scale factor. So during the construction stages, if we want to consider the changes of the material property, section property, we can use this. And it is generally used for considering crack in the high-rise building, which means that its stiffness will be reduced in a certain stage. When you use the plate element for the walls or slab, also plate offset can be used. When you define the thickness, we can specify the plate offset. And if we want to include the basement floors, we can consider the soil interaction using the point spring support or surface spring support. So in the boundary, if we go to the model again, if we want to model piles or the mat foundation, then in boundary, we have the point spring support. So we can consider the compression only or multilinear type soil stiffness. Also for the transport girder, we can assign the tendon in the beam. One limitation of Gen is we can consider the tendon only in the beam element, so not in the plate element. So if we need to use the tendon in the slab, in this case, we need to add the dummy beam along with the plate element, and then tendon can be entered to that dummy beam. And there are some issues that I wanted to tell you. Is before the demonstration, I want to tell you some of the notes we need to be careful when we use the construction stage analysis. This issue has been mainly it was from the technical support with the TT when we do in the previous project like Kingdom Tower or some other projects. So this is also a common issue many users make the mistake. Firstly, I mentioned that when we use the user-defined creep function, we need to generate several creep functions, not only one or two functions, with the different loading ages. So since each of the elements will have different ages, so in order to have the accurate results as the program do the linear interpolation, at least 5 or 10 functions is recommended. In case of the DB creep function like CBFIP or ACI Eurocode, when we use the database creep function, program have the 48 functions internally, and using these 48 functions, we do the linear interpolation. So if we want to have accurate results, more number of functions is recommended. with the different loading age. And when we do the technical support for the Kingdom Tower previously, we found one error in the program. There was some limitation in the clip convergency when we use the triangle shell element. And this has been resolved. So if we use the program after the June 2012, then there will be no problem with the triangle elements with the clip convergency. And when we use the self-weight function in MIDAS Gen, in order to consider the self-weight of the structure, we have the self-weight function. So we only need to consider the -1 value for the self-weight, and then using the weight density of the material and its geometry, then program automatically calculate the weight of the structure. This self-weight needs to be activated only one stage. So this self-weight is included in the CS1 load group. And this CS1 load group is activated in first stage. So even though this element activated in next stage, the other element, so each self-weight will be automatically considered in the proper stages by activating the self-weight in the first stage. But we need to be careful when we use this self-weight in the construction stage. The self-weight should be always activated at the first day of a certain stage. So, as I mentioned previously, we can specify the active day for the load group, but in case of the self-weight, we always select the first day in order to have the correct analysis result. Otherwise, the self-weight will be incorrectly calculated. So, self-weight should be always considered activated in the first 2 days. So we cannot make the additional stage and then activate the self-weight in the additional stage. If we want to activate in some days after, then we need to divide the stages. So make one more stage, and then in the next stage, we need to activate the self-weight in the first day of the next stage. So self-weight should be activated always in the first day. And we can consider the floor diaphragm. In the story data, you can find it in the model building story. Not only the story level, but also we can consider the floor diaphragm in here. This floor diaphragm we can consider from the second story, but first floor generally it is not considered because we already have the support at the first floor. So in the first floor, since there is already restraint, if we make the floor diaphragm, then it will be doubled for the restraint, so it conflicts to each other. So if I try to consider it in the first floor, which has the support node, and if I try to perform analysis, program will give the warning as you just checked. The constraint degree of freedom of the slab node are automatically released. So this will be automatically released. So in order to prevent this warning, Generally, we do not consider the floor diaphragm for the first story. And there is one more thing we need to be careful when we use the story diaphragm in the construction stage. When we make the group, I mentioned that we can make the boundary group and then activate or deactivate them during the stages. So that boundary group can be specified. For example, there is the menu for the boundary group for each of the boundary menu. But in case of the floor diaphragm is considered from here, and there is no related menu for the making group. There is another menu we need to be careful. Story diaphragm group for construction stage. So when we want to consider the diaphragm during the stage, we always make the group in here, and this group, for example, diaphragm second floor, third floor, so on. This group should be activated or deactivated during the stage. As you can see, for each of the stage, so diaphragm group is not considered with the story data dialog box, so this should be separately defined using this function. So this one is another issue we need to be careful when we use the story diaphragm in the construction stage analysis. And most of the engineers have, when there is the error in the analysis, or if you obtain unreasonable forces or displacement as a result of the construction stage, generally it is occurred because of the improper boundary condition or improper nodal connectivity. So during the construction stage, as many elements are activated or deactivated during the stages, so it's very common mistake. Some of the element is incorrectly activated without any support, and it can make the singularity error or unreasonable displacement. So in that case, during the analysis, program will give you the singularity error in this analysis message window. So we need to go to the first stage that error has been occurred, and then what we can do is we can save the current stage as a static analysis. So only one single stage, for example, fifth stage, if I had the singularity error in this stage, but I'm not sure which model has been incorrectly entered, then I can save the current stage. Then without the construction stage data, without construction stage, this model has been entered, then we can try to perform analysis whether this state is complete or not, and we can check more easily in simple state. So let me briefly have the demonstration for the construction stages. So I'm going to use the simple model file that I showed you so far. I will use this model, and as you have the experience of the general features, so I'm not going to show you how to make the element or how to make the boundary load, so on. I will just jump to the construction stage features. Before we make the construction stage, let's check the construction schedule of our sample model. So in here, one by one each story will be installed, and this white picture represents the formwork, and this gray one represents the concrete. So third day concrete will be casted, and still formwork is there. From the day of the concrete casting, after 19 days, its formwork will be removed. So now it is activated. So when element is activated, this day will be first stage in MIDAS gen with the concrete age as 19 days. And then next element will be activated in this 29th day, which has the 7 days difference. So duration of the first stage will be 7 days. 7-day duration at the first stage, and concrete age is 19. And it goes with the same manner, so on. So we can make the group one by one, and then we can activate or deactivate from this dialog box, or we can use the wizard. So since this is some regular rule for the construction stage, I will use the wizard. The wizard can be generated under the load, construction stage, analysis data, and wizard. So from here, we have the automatic generation feature. I want to consider the dead load, and each story will be increased in the different stage one by one. As I mentioned, one stage duration will be 7 days, and its member age will be 19 days. As we checked, from the casting of the concrete, its age is 19, and until the next element is activated, its time gap is 7 days. And superimposed dead load we want to consider, and this superimposed dead load, which is applied from the 71 days from the activating from the first element, and 1 to third story apply at the same time, and 4 to 6, 7 to 9. So for 3 different stories, it is applied at the same time. So which means story increment is 3, and starting day will be 71, and day increment 3 day, which means the 3 day after the other 3 story, 3 day after the other 3 story, so on. And live loads we want to consider at 112 days in a dummy stage. So live load for the entire story we want to apply at the same time in a 112 starting day, and day increment, it is applied at once, so this value is not important. It is not used. Okay. So once I click OK, we can see the groups has been generated. If we see the structure, so from the first story, story, and then up to the dummy stage, which is the live load. And as I mentioned, if we use this wizard, we need this to consider the story diaphragm group. This has been automatically entered. We want to consider the time-dependent effect. So we can go to the model property time-dependent clip shrinkage function. Sorry, I want to use the database, not the user-defined function. So I will go to here. Previous one was the user-defined function. This one is for the database of the program. Let's use the ACI. Specify the proper strength of the concrete. After define the required data, then if we click show results, we can see the clip coefficient shrinkage strains in here. Apply. Sorry. As I mentioned, when we use the construction stage model, we always enter or modify certain data in the base stage. So let me change the stage to the base, and then I will define it once again. The ACI. So we can check and apply. And I want to enter column clip and shrinkage with different compressive strengths and with different volume surface ratio. Apply. And finally, one more for the walls. Wall has the same compressive strength, but its volume surface ratio is different. Okay. Similarly, we can enter the compressive strength data. We can check the changes of the compressive strength with the days. One more function I will define. Okay, then as I mentioned, what we need to do is making the link. So in the time-dependent material link for the girders, right? Similarly for the columns and walls. So the time-dependent data has been now entered. In the construction stage analysis control, as I mentioned, we will consider the time-dependent effect, and we can distinguish the live load data from the merged dead load. So I will select the live load here. Okay. And if we want to see the first step result, we can click on this additional step. But if we want to check only the last step, then we do not need After doing it, if we perform analysis, we can check the results. So with the different stages, for example, if I want to check the forces, you can see the summation, and with the different stages, even the dummy stage, which is from the 100 days from the construction. If we want to check the additional creep and shrinkage effects, for example, 3 years after, then we can simply add the construction stage with the certain duration without activating certain element or load. So only adding the construction stage, like we can add final stage and duration, for example, 1,000 days, then we can check the creep and shrinkage long-term effect from this. So we do not need to activate certain element, boundary, or load. So in the final stage, similarly, we can check the creep or shrinkage effect, and this can be checked for each component for different construction stage in the table. For the dead load, live load, creep, and shrinkage, and or summation. With a different stage, we can specify as well. Here we have the column shortening graph. So as we previously checked, this is the column in this position. So what will be the shortening of this column? So we can check the subsequent shortening because it is the RC structure. In the final stage, so we can see the column shortening results, and as I mentioned, it can be saved in the image, text, or Excel data. So this is the main issue for the construction stage. And so now I would like to move to the floor diaphragm. But if you have any question, you can use the questions window for the questions. So I will move to the floor diaphragm. Okay, so I will move to floor vibration. So I think you have already received our tutorial file. So I would like to explain with this sample model file. Similarly, I will not do any modeling for this. Just one thing I want to mention is, if you see our tutorial, it is a bit out of date. So at the time, MIDAS did not provide the auto mesh feature. So we needed to use another tool for these plate meshes, but at the moment, MIDAS Gen provides the auto mesh. So by making certain boundary, then we can make the meshes inside of Gen. We do not need to use the mesh program separately. And in this model, so it is composed of the slab, RC slab, and the steel girders and columns and core walls. So slab and walls has been modeled with the plate element, and girders and column is composed of the beam element. For the joint between the columns, for example, this node is continued for the columns and plate, but it is concentrated to one node too much. So, and it is different from the realistic state because our FEM model cannot consider the area of the column. So we used the rigid link. So connected nodes has been rigidly connected to this node. So it will move all together as a rigid diaphragm in this small field. It's the same for the three different parts for which column is connected to the beam. So this can represent the area of the column. So stress will not concentrate too much in a certain one node. And for the boundary condition, we entered support, as you can see here. This is only one partial part of the entire structure. So we just simulated some continued part and the end part. So if we see for the end of the slab, they can move to, for this edge, they can move to the X direction, but its Y direction movement is restrained. Similarly, for this edge, their movement in the X direction has been restrained, and also moment about the Y axis is restrained. And for the walls, their movement has been restrained except the movement in the gravity direction. In case of the column, bottom, all three DOF is restrained, just like the bottom of the walls, and top, only the Z-axis movement is allowed. After assigning the proper boundary condition, and in case of the joint between the slab and girder, since the neutral axis of the beam is center of the element, so it is modeled like this, but in the realistic state, there is the slab and with the certain hunch, and then bottom of the slab, this beam will be installed. So real position will be quite below from this position. So in order to represent that, we have added the beam and offset feature. So which means the top of the beam, actually this center will move to this much. So we need to assume that this will move like this much below, which means the top of the beam and bottom of the slab will be connected each other with a certain gap of the hunch. So beam and offset has been added, Actually, this beam offset can be simulated using the section offset feature as well. In the section property dialog box, there is the section offset. So center top, or we can specify the vertical offset position. So by entering certain value in here, the same effect can be simulated. So we can use this change offset function or beam offset function. The effect, member force, everything will be same between two. And firstly, we have considered the pressure load for the dead load. And we have eigenvalue analysis with a certain number of frequency. After that, then this load has been used in order to simulate the mass. So load to mass feature has been used with the scale factor 1. So this load is considered as a mass in this structure. So this load represents the dead load of the structure, and this has been converted to the mass. Then after we perform analysis, we want to check the eigenvalue result first. If we go to the vibration mode shape, we can see the neutral period and its mode shape. But in case of the mode 2, it is not governed for our desired position, for which we want to consider the working load in this direction. So this is different from our expectation. And mode 3, 4, mode 4 again, this meets our expectation of the desired mode. So mode 1 and 4 was our expected mode. Similarly, if we check one by one, if we exclude the mode which has the local deformation for the end of the slab, then we have the 4 modes. So if we see the multi-modes, so these modes can be checked. And then if we move to the table, we can see more values for the frequency and period. So first mode and so if we see the multi-mode one by one, actually the expectation of our mode is 1, 4, 8, and 13. So if we see each mode, so we can see its mode shape is expected in the certain area that we will apply the dynamic nodal load. So we will use this lizard mode 14813. So if we bring the data, I want to bring this data to Excel. So I just simply pasted it. So based on these four modes, let's try to perform the floor vibration analysis. We need to determine the period for the pedestrian load. That period of the pedestrian load is generally known as the 1.6 to 2.5 Hertz. If we see my simple note, this mode is different from our mode. So this mode is 14813, but other frequency is generally same. So generally the frequency of the pedestrian load is known as this range. And our first mode frequency is 9.58. So we can divide with a certain value. We can divide this first frequency value by an integer. For example, if we divide this frequency to 5, we will have the frequency 1.916. So this frequency will be used for our pedestrian load, which meets this general range. So if in the structure, firstly we will obtain our frequency, and then we can divide with a certain integer in order to have the frequency inside of this range. So that frequency will be used for our pedestrian load frequency. And the time step, generally this time step needs to be used as a 10% of the period, smallest period. So in our time eigenvalue analysis results, the smallest period is 0.03 second. So as a 10% of this, we will use the time step as 0.003 second. So we determined the desired frequency of the load and the time step. Based on this data, we can enter the time function. So using this model, we want to enter the floor vibration data. So we will go to time forcing function. MIDAS Gen provides the database for the working load or learning. Bauman, EFC, and AIJ we can specify. So our working frequency as I mentioned, we want to consider it as 1.196 and time step 0.003. After enter this, we can have the certain time history function for 1 steps. So this function will be applied for each different node using the dynamic nodal load. Before that, we want to enter the time history load case. This will be the linear modal analysis. And at the time, we want to consider 7.5 seconds. Time history increment 0.003 is same. And save output. For each step, we want to save output. And the damping ratio, we want to consider 5%. Then, for simulating the working load, we can use dynamic nodal load with entering the function that we just defined using the AIJ standard. The direction of the load will be Z direction, and we can specify different arrival time starting from the 0 second for the node number, this one. So just like this, we can also enter the data from the table. So on. So for this node, like this gap, we want to enter the dynamic nodal load for this. As you can see, with the certain interval, we want to enter the dynamic nodal load one by one with the different arrival time. So that can be entered. So in the same way, I predefined the dynamic nodal load for entire nodes. So if we display this data for each of the nodes, this dynamic nodal load has been entered with the different arrival time. After that, we can check the results. So we can perform analysis, and then as a result of the time history analysis, if we go to the displacement contour for the time history results, we can check the maximum displacement or acceleration nodes. So this is the maximum deformation, and the maximum node number is this number, 1684. Also for the maximum acceleration, node number is 1007. The node in here has the maximum acceleration. And this node has the maximum displacement. More detailed value can be checked in the text or graph. Firstly, for the graph, we can define the displacement of the node which makes the maximum displacement in the z direction. We want to check the displacement and the reference point is ground point. Time history root case is 1. After define it, then we can check the graph. So with the time domain, we can see how this node will behave, and this value can be checked with the frequent domain. And the peak displacement can be checked from here. Similarly, for the maximum acceleration node, we can see its behave, and we can check the period using this curve, and peak acceleration can be checked from this. So the peak acceleration in our example is 9.94. And this 9.94 was if we checked our previous time history eigenvalue analysis results. This value was the most closed frequency from our first mode shape. So with the time forcing function that we used, with the 1.196 Hz, we have the acceleration as you can see here, and its peak acceleration is close to value to the first mode frequency. And MIDAS Gen provides the function to evaluate the structure with the AIJ standard. So again, if we go to the time history graph, for example, the acceleration, here we can see the serviceability check graph. This too is based on the AIJ standard. So for the acceleration, this represents the point for our structure, and this is the limit that AIJ standard provides. For example, this V1.5. This state is for general vibration for the meeting room, and 0.5 is general vibration for the residential purpose. So since our structure is in here, so if our limitation was in the residential building, then it is not satisfied. But if it was for this general office, then it is satisfied. So based on the AIJ standard, we can evaluate our structure status. It's same for the displacement. So for the residential building, the displacement is not satisfied, but the general office, it is satisfied. So this serviceability check function is provided as per the AIJ standard. So we can use these features, and if you are using the AIJ standard, you may know the limitation that V075 or V1.5 so on. So we can simulate the structure status using that. Other feature for the time history function is same. So we can check the behavior of the structure with the different time step. And this can be simulated with the animation. So for the displacement or velocity acceleration with the different time step, we can check the exact value from here or in the table. So the vibration can be simulated with the animation, as you can see. Since it takes some time for the loading, so I just simulated in a short time. But by adjusting this increment time, we can check this behavior in the animation. And this can be checked with the table, as you can see. So for the entire element, what will be the displacement or acceleration maximum? We can check with corresponding time step. Okay, so that's it for the floor vibration. Do you have any questions so far? Any question about MIDAS Gen will be okay. If you have any question, please let me know. Okay. Okay, thank you very much for joining today.